Hello, physics class. Today we're going to be talking about waves, and you should have done the notes for section 14.2 on your own, so I hope you have your notes available, and you just need to add to them as needed. Some of y'all had really nice, well thought out notes, and some of you just did the tiniest bare minimum. So if that's you, make sure you really fill in some of the details that you certainly probably missed. So let's talk about waves in general, and we're going to be talking about mechanical waves. Now let me back up and say that a wave is caused by vibrations. And so we have other waves besides mechanical waves like light and things like that. But mechanical waves are things that physically move matter up and down, so they require matter. And your book divides mechanical waves into two basic types. One type is what we would normally think of when we think of a wave, and this is a transverse wave. And this can be a little bit misleading because electromagnetic waves that do not require a medium also have this same transverse shape. But you can still have mechanical waves that have this shape too. And imagine taking like a rope or a string, maybe like a jump rope, and stretching it all the way out, and you just physically move it up and down, and you make this pattern. That would be a mechanical transverse wave. When we talk about electromagnetic waves, those are going to have that same transverse shape, but they don't require matter if they're electromagnetic. But this section is about mechanical waves, so imagine more a rope or a string doing this motion than like a light wave. And then also I want to point out that waves move energy. Like if you have a jump rope and you're kind of making it go crazy up and down, the particles in the jump rope don't move along. They're just going up and down as the energy passes through them. So I want to emphasize the fact that waves transfer energy, not matter. And then the other type of mechanical wave, your book calls it a longitudinal wave. I hate that name. I don't know why they did that. Most other books call them compressional waves. And these would be like the waves on a slinky or a spring. And then also like air particles when we have sound waves. Imagine like this bottom one is a column of air. And as the sound wave goes through it, of course I just showed a small section, but you have areas where the air particles would be spread out, and then this would be a compression, and then another spread out section, which is called a rarefaction, by the way, and then another compression. And then I actually have a slinky. I know you're so impressed, right? If you have a slinky, you can make a slinky do a transverse wave like that, but you can also make a slinky do a compressional wave. And so basically you would stretch it out. This is like a rarefaction, and then like areas where it's compressed would be the compression. So I'm going to try to do this and see how it translates to being on the screen. I don't know. We'll see how this goes. You can't really see it. But basically there would be areas as the energy passed through the slinky that would be like this, and then there would be some that would be compressed. It's hard for me to do this with just two hands. I need like three hands. And then there would be areas where it would be stretched out, and then areas where it would be, I can't do it with two hands, all compressed like that. And so as energy passes along the slinky in this way, like a back and forth motion, okay, that would be transmission of energy. And again, the slinky itself is basically staying in the same place. It's just moving back and forth, and the energy is what's passing through. And so again, your book calls it a longitudinal wave. I like the term compressional wave because it's filled with compressions in stretched out areas that we call rarefaction. And then the third type of wave that I do want to mention, and we're not going to talk a lot about it here in physics, but it's a surface wave in water. And so if you go to the ocean or the beach, you're going to see waves along the surface of the water. And if you like to surf or just play around in the surf, whatever, you've experienced this. And I do want to point out the water is not moving much. It's just going in circular patterns. And if you want to get a better look at that, this is on page 389. Yeah. So we're not going to do any equations or anything associated with the surface waves of water, but I do want to point out that it's kind of like a combination between the longitudinal and transverse waves. Also, seismic waves caused by earthquakes, those exhibit many of the qualities of being that circular motion that the surface waves of water will. Okay, so let's talk about a wave in general, and this is going to be like a throwback to probably physical science, or even like, I don't know what grade you covered waves in middle school, but we'll go ahead and go through some of these. And this is a transverse wave, and then the top positions, specifically the centers of these are the crests. So that's the crest of the wave. And if you want to follow along, some of these are going to be labeled on page 391, but it's fine. I think you've already had this material anyway. And then the bottom section, it's really hard to do this like backwards, but that's okay. These are the troughs, Troughs. Okay, and then this middle line going through it, this would be what the medium would be at if no energy was passing through it. So this is the rest position or equilibrium position. And so we're envisioning the wave going through, and the energy is starting over here and it's going that way. That's how the energy is traveling through this wave, and it's making the matter vibrate basically up and down. And so rest position would be if no energy was passing through it whatsoever. And then the amount that it rises off the rest position here, or that it lowers from the rest position, so here or here, that would be the amplitude. The more energy that's going through the wave, the greater the disturbance, the higher the amplitude. The less energy, like if a little bit of energy was going through here, it would just be a tiny little hump and then back to the equilibrium, and then a tiny little hump right there. And so the higher the amplitude, the greater the energy. And then the other thing that we need to cover on this is wavelength. So let me change markers. For wavelength, you need to look for consecutive crests or consecutive troughs. And so I'm just going to pick these two crests right here. And then I'm going to draw an imaginary line. Of course, we would just measure the distance between here and here. And this distance should be in meters for your SI unit. And the symbol for this one is pretty cool. We get to use another letter of the Greek alphabet. It's called lambda, Lambda. And so we actually use that for wavelength instead of a W, because we have W for too many things like weight, work, omega kind of looks like a W for angular velocity. Like, we're done with the W. So they moved on to a Greek letter, lambda. All right, and then let me go through a few other things, and then we'll do a math problem. Of course, it's not just one math problem. We've got multiple math problems. And let's talk about frequency. Let me review period, though, really fast. I think we have period in 14.1 notes. The period is the time it takes for a wave to make one complete cycle, and it's measured in seconds. Now, of course, it can be so long that you could actually say it in minutes, but or even longer than that. But the typical SI unit would be second for that. Frequency is similar but different. Okay, so frequency, basically you pick a position and it's the number of waves that travel past that in 1 second. And it does not have to be a whole number. In fact, most of the time it's not. It could be like 2.8 or 0.00057, whatever. It can be way different than just a whole number. The SI unit for this is one that you've probably heard of before. It's called hertz, and we abbreviate it capital H lowercase z. And 1 hertz is equal to 1 over a second, or seconds to the -1, or, I have that twice, duh. Okay, forget that. I didn't realize I wrote that. And then the symbol is like you would think, F, lowercase f. And then here is the formula. We'll need to come back to this for math stuff later on. But the frequency is equal to 1 over the period. And since period is measured in seconds, then it makes sense that a hertz is equal to 1 over second. All right, so that's frequency. And then I also want to talk about wavelength. And I already mentioned that wavelength has the cool symbol lambda. Again, that's the Greek letter lambda. If you've ever seen that movie, and I'm not endorsing this movie at all, but it's called Revenge of the Nerds. They were nerds and they decided to form their own fraternity. And so they, you know how fraternities are based on Greek letters like Alpha, Omega, Pi or whatever. They did lambda, lambda, lambda. So just a little bit of movie trivia there. And again, I'm not endorsing that movie, but I'm just saying that you might recognize lambda from that if you have seen that movie. And then the SI unit I mentioned earlier was meter. And then here's the formula for calculating wavelength. So we've got lambda, and then the V is wave speed, which is interchangeable with velocity. That's going to be meters per second. So how many meters it goes in 1 second. And then the frequency, okay, is the number of waves that travel in 1 second. That's going to be equal to our wavelength, and that should be a meter. So meters, hertz, meters per second for the velocity. All right, let's check out our one sample problem, which is actually way more than one sample problem. We're going to be on page 392, so please add these to your notes. And if you need to pause the video to get your book and get your calculator and all that kind of stuff, please work through these because I don't think they're super hard, but I could see where if you didn't bother to do any of them and then you went to do on the quiz, you may not really be familiar with what to do. So please follow along. Okay, so I'm going to be on page 392. Okay, and we're going to do example problem 3, which is really 1, 2, 3, 4, 5 problems. Don't you just love that? Okay, so let's talk about what the problem actually says. And it says that we're dealing with a sound wave, so we know we're dealing with one of our mechanical waves. The sound wave would actually look like, where's my particles? Yeah, it would actually look like this, kind of. Where you've got air that's compressing and stretching out and stuff like that. So just kind of visualize that if you would. And the problem on page 392, it's at the very top of the page, it says a sound wave has a frequency of 192 hertz and travels the length of a football field, which is 91.4 meters, and it happens in 0.271 seconds. And so write down all of your givens. There we go. So again, I'm just going to kind of move through these, but pause it if you need more time to write. And then A says, what is the speed of the wave? And so we only need to solve for V. So the speed of the wave, this is an oldie but a goodie. Remember, velocity is distance divided by time, or change in distance divided by change in time. And we have both of those. You can plug that in and see. Again, pause your video because I'm just going to roll right on through. Okay, and then B, you're supposed to find the wavelength. This is where we use our new formula. Remember, this one was like a blast from the past, but it's something that you should readily remember. For the wavelength, you have to use the brand new formula that I just introduced today in this section. And we're going to use our V from here. So you know what happens if you get this wrong? You have no hope. So please be careful and do this one correctly. I'll try to give partial credit, but online it's even harder. I've found that out. So just do it right and we'll all be happy. And then frequency, it gave you the frequency in the problem. And so you're basically going to set it up like this, and then you can get your answer. Please pause if you need more time. Okay, moving right on through with C, we're supposed to find the period of the wave. I love this formula because it's super easy. The period is just equal to the inverse of their frequency. And so you just have to do 1 over F. And again, the F is given to you in the problem. Yes. So you should be able to get C right even if you got A and B wrong. And so go ahead and pause if you need more time. Remember, you're adding these to your notes. And then D, if the frequency were changed, now it's only 442 hertz. Oh, actually they upped it to 442. What would be the new wavelength and period? And so you already figured out the velocity from above. And so you just have to take the same value. The velocity didn't change. The speed didn't change. So you just take the velocity and divide it by your new frequency. And then that's what you get there for wavelength. And then the period, you could get this right independently. You just take 1 over the new frequency and you get the period there. So if you need more time, pause the video. Okay. And I'm going to do like a keyword for today. The keyword for today is slinky. So if you watch this video, you're going to see a question about that. I guess if you don't watch the video, you'll still see a question about that. So don't tell your friends because they should have watched the video. Just if they ask you, just say, well, you should watch the video. You can find out. But please respond to this. And I think I'm going to go ahead. I feel like this material is pretty easy, so I'm going to go ahead and push through to do a quiz. Actually, not a quiz. You're going to have a homework section and then a quiz on this. But I think the math is pretty easy, and I feel confident that all of y'all are going to do a great job. And I hope you are continuing to do well. Continue to do all the hard work that you've been doing and press through, because we don't really have that many days left. So that's pretty exciting. And I'll see you guys again soon, hopefully.